Hello, everyone. Thanks for having me here and inviting Continuum to come and speak about our work in the open source community. And so first question, how many of you are Python users or have used Python? And how many of you have used Anaconda or Conda? Great. I'm hoping to increase that to the number of the first group. Hopefully some of the things I showed today will show that. It's on. Yep, thank you. So quickly, a few things about Continuum Analytics. We're based in Austin, Texas, where I work, and we have offices in New York, Vancouver, and we have folks remote all over the globe, 130 employees. We do, some of our developers are full-time working in open source with some of the tools I'll show today. And this is all part of the Open Data Science platform, which includes Python and R, but really extends to many other types of languages. So hopefully this is action-packed. I have lots of demos to show and neat things of all the foundational components that we're working in Anaconda. So an overview of how this is structured. First, I'll talk about what is open data science and what is that composed of and what kinds of tools are available to us. And then I'll talk about some of the foundational components. So I'll talk about packaging, optimization, visualization, parallelization. Some people think of Python as a scripting language, but it's much more. It's a glue language, and there's many foundational pieces that we're working on in Continuum that have each their own communities and have created very strong tooling for different verticals like biomedical engineering and astronomy and so on, finance and so on. And then I'll show some demos that are running on a live cluster for distributed computations in Python that are running on a Hadoop cluster, and then summarize all of those things. So we'll start with open data science. What is open data science? So as we work with our users and customers, they're data scientists, analysts, DevOps, and so on, they really want a few core things. So they want interactivity. They want to be able to interact with their data. They don't want to run overnight batch jobs. They want to have very fast queries that are interactive, where they're able to collaborate and share results in a much faster workflow. They also want collaboration. So some of the tooling I'm going to show talks about notebooks and talks about how we can share that through Anaconda services or other services, and then really integration, right? So the thing about Anaconda and Conda, which I'll talk about in more detail later, are that they are powered by Python, but they're certainly not limited to Python. Python is a great glue language and enables us to integrate things like R, MATLAB, SAS, Excel, that a lot of our users and customers have their data spread all over the place. And so with these core values in mind for open data science, we'll talk about how Python addresses that, how Anaconda addresses that, especially in the open source world. So regardless of the news you might read that machine learning this, machine learning that, data science is not just machine learning, right? It's machine learning, business intelligence, distributed computing, web technologies, and scientific computing. And it's really the unification of all of these different things and components that are the many dimensions of a data science or an analytics team. And data science is very interdisciplinary, right? So just in this room, we have many, many different disciplines, folks I've been talking to. Some come from scientific computing, others come from business. And really, a data scientist or a data science team is expected to have some well-rounded representation of these dimensions. So for machine learning, that might involve, creating machine learning models, classification, distributed systems. You might have folks that are versed in Hadoop and Spark, or some of the distributed engines, and so on. So really, we want to unify these dimensions and give them a platform that allows them to connect experts to data. So on a data science team, you can look at different types of personas, right? So some of you may be able to relate to one or more of these personas in your own line of work. So business analyst working with spreadsheets, or you might be a data scientist expected to do machine learning and visualization, a developer who's working in many different programming languages and environments, a data engineer who's moving and doing ETL on data, and then DevOps, who's actually productionizing these models once they're done. So we want this team to work in cycles. We want them to work all together using the right technology and tools for each persona shown here. So open data science is, you can think of it like an inclusive movement that makes open source tools of data science work together. So often our users or customers might say, well, there's technology A and technology B, which one should we use? We say, well, use both and use them in a way that's meaningful for your workflow and use the best tool for the job. And so we're really looking for a connected ecosystem, and you'll see this surfaced in some of the tools I'll show later. So open data science means availability, innovation, interoperability, transparency. So it's sort of a movement from siloed applications, siloed data, into a platform where everyone on the team is able to collaborate and interact and share results. So, to the more specifics of this ecosystem, I'll talk more about the work that's been done in open source over the past few years. So, if we look at those 5 dimensions, in machine learning statistics, there are things like scikit-learn, stats models, TensorFlow more recently from Google, Theano, Lasagne. In business intelligence, there are things like pandas, Excel connectors to Python, Blaze, distributed systems. Spark has PySpark and SparkR. There are distributed systems like Dask. There are task management systems like Luigi and Airflow. Then there's web technologies and scientific computing, NumPy, SciPy. So all of these have come from different needs in the open source community. And what we're interested in is how to unify those in a platform. And this is where Anaconda as a distribution and as a data science, open data science platform allows you to do that. So all of these tools I'm showing here, Python is the common language, right? It's the thing that unites them in not only in APIs, but also in data structures, right? So most of these tools work with NumPy and pandas at the most basic level. And that's something that's really nice when I show the scientific Python ecosystem later, that we're able to interoperate. But we realize Python is not the only language, right? There are many, many others. R, C++, Fortran, Excel, SQL. So there's many other tools that work in this ecosystem. The great thing about Python is a great glue language, right? So whether your workflow has things in Excel and big data and Fortran, we can make that all happen. And hopefully some of the workflows I show you today exemplify that. So Anaconda is the open data science platform that brings together all these technologies. It's powered by Python, and it lets us work in interactive, collaborative environments where we can quickly iterate on whether we have small data, medium data, or big data. It allows us to flexibly work with those different environments and then deploy that into production. So I'm going to talk about some Continuum-supported foundational open source components to kind of walk you through the different, what we see as building blocks that we then deliver to our customers and users to be able to do whatever they need in this flexible platform. So the idea is we don't have just one cookie-cutter solution, but we have these many foundational components that different verticals can use and implement in their own way. And you'll see examples of that later on. So for package management, I'll talk about Conda and Anaconda and what those are. For data analysis, things like NumPy, SciPy, Pandas, these are all sort of very basic, very fundamental libraries for doing numerical scientific calculations. Numba for optimization. Visualization, there's many areas to talk about there, and I'll show some demonstrations. And then Dask for parallelization. So these are all Continuum supported. They are all on GitHub. These are all permissively licensed, BSD licensed. So this is what makes up the core of Anaconda, in addition to the many other packages available. So first, we'll talk about packaging. Packaging is a huge pain for folks working in scientific computing in Python. So our solution to this was when Continuum started in 2012, Conda was one of the first deliverables and the distribution that came of the Conda packages. So what is a Conda package? A Conda package is powered by Python, but can be anything. It's just a tarball with metadata. So it can be a Python package, it can be C, Fortran, anything really, Scala packages, Java packages. What this does is it's an open source spec for cross-platform pre-compiled binaries, right? And I'll show a quick demonstration of this in a minute. But what it means is if I install something like NumPy, which has dependencies in C and Fortran on Windows, Mac, or Linux, I don't have to have that tool chain available. You can Conda install it with one command, and you're done. The second neat thing that it does is sandboxing. So you can have multiple Python environments that are completely separate from your framework installation of Python and use those independently. So if you need Python 2, Python 3, and R installed on your laptop, Windows, Mac, or Linux, you can do that with Conda. So Conda is the package manager and the packaging spec that drives all of this. You can see here the languages it supports, it's cross-platform, and Conda itself is open source. So the Conda is the package manager, Anaconda is the distribution. So Anaconda comes out of the box free for Windows, Linux, and Mac. It includes more than 100 popular packages out of the box and access up to 700 plus packages for R and Python. These are optimized and compiled, so if you download Anaconda today, you'll get NumPy and SciPy that are compiled with the Intel math kernel library, MKL, for free. So you get that optimized right out of the box, which can lead to 3 to 30 times speed up for numerical operations. So that's redistributable, free. Of course, Anaconda is powered by the Conda package manager. So if you install Anaconda, you can Conda install many different things. It's cross-platform, and I'll show a quick demo of that now. So if I have my terminal here on my laptop, I can list the Conda environments. So if I list Conda environments, I can see I have a few different Conda environments. And say I have one with Python 2.7. So I can activate that environment, Py27. So now if I start an IPython shell, you can see here I'm running Python 2.7. This is completely separate from the framework installation. So no matter what OS version I have, maybe CentOS 5, I can install separate Python 3, Python 2 as I want. So here, if I say I want to import NumPy, I don't have NumPy, so I can exit and I can Conda install NumPy, SciPy, Pandas with one command and confirm that. And I have those installed, right? So that's retrieving it from the Continuum free repository, and I just installed those on the Mac with their dependencies in C and Fortran without having to worry about that tool chain. This is something where pip, if you're familiar with pip, the Python package manager, might fail you depending on what version or what system, what operating system you're on, or what tool chain you have available. So now, if I want to create a new environment, I can Conda create. Let's say I want to make an environment with Python 3.5. So I can do that, and I can include the Jupyter notebook with that. So what it's doing now is creating a new sandbox, and it's installing the things I need for Python 3.5 and Jupyter. Once that's done, I can activate that environment, Py35. Now I'm working in Python 3.5. That's simple, it's to switch between environments. So if I have one project with certain dependencies, another project, I can easily switch between those. Then when I go to deploy that using Docker or AWS or whatever it is, I can have that environment spec included. So that's a very quick sort of demo of Conda, and it's sort of the basics, but it's very powerful. From there, I can spin up a Jupyter notebook, and I'm suddenly working in a Python 3 environment with a Jupyter notebook. So I have the Python 3 kernel available, and I can import things from here from that environment. So that's the basics of Conda and Anaconda as a distribution and as a package manager. And that has solved more pain. We hear customers, even to this day, thank you for this tool. I don't no longer have to maintain this crazy build chain on each computer. I can just have binary. So a lot of customers and users create their own packages, which leads to Conda Forge. So Conda Forge is something that spun up in the last year. And this is really neat. So if you think about Red Hat and CentOS, this is sort of like Anaconda and Conda Forge, right? So Continuum, we do build packages, and we release Anaconda with our built-in test packages. Some folks outside of Continuum created a community channel called Conda Forge, and it's a very neat automated system that allows you to build things on Windows, Mac, Linux, using Travis CI, using AppVeyor, using Circle CI. So you can actually submit a recipe to Conda Forge completely outside of Continuum, and it will build that recipe, and it will build the dependencies, whether it's C or Fortran, whatever it is, and they're using Docker images for that. And what that means is it's a community-driven repository where folks are creating and contributing to, just like CentOS has a repository. So this is very exciting. It's basically a combination of a channel, a community channel, and built packages that are tested automatically. They have a very nice automation system that makes, it checks your recipes, it compiles them, it tells you if there's errors. So this is a very excellent effort, and we're actually migrating many of the tools I'll show here. We're actually migrating them to Conda Forge to be part of this community movement. So this is a very nice thing that has happened recently. On to optimization. So you may be wondering why I'm talking about optimization in Python, right? People think Python interpreted language is slow. I'm here to show you that's not the case. So Python for high performance, why would we even consider that? Well, actually, the same reasons that we consider Python as a programming language, we can consider for a high performance language. So it's easy to use, easy syntax, the batteries are included, it ships with lots of basic functions in the standard library, and also has access to many of the other libraries that I showed earlier. And there's innovations from open source, which leads me to how do you get high performance when you need it in Python? And Continuum's answer to that is an open source project called Numba. Maybe you've heard of this. This is it's a just-in-time compiler that ships your code from Python to the LLVM on the fly. What that means is portability. So if you're working on an Intel or AMD CPU, or you're working on a GPU like NVIDIA, it will compile to that target and optimize for that target at runtime. So what this means is it compiles your Python scripts directly into machine code, and it can increase your performance from 2 to 200 times. I realize that's a big range. The reason is, if you're already using things like NumPy arrays or pandas data frames, these are already written in C. We take advantage of the fact that we've released the global interpreter lock, and you may see a 2-time speed up, which is sometimes a big deal for a customer. Or in cases where you have naive loops, like here, you can see speed ups on the order of 10 or 100 times speed up. And the nice thing about Numba is it works as a decorator. So you see that decorator up top, and I'll show an example on the next slide, is we put a decorator around our function. It looks at the function signature, the types, and it figures out how to optimize that on the fly. And then you see increased performance. So what that might look like in the real world is you might have some code with NumPy. So we have some loops, so you can see lots of nested for loops. And in this case, we're going to add the Numba JIT decorator, right? We've added 2 lines of code here. And in cases like this, you might see 10 to 100 times speed up just with that. So the idea of Numba is that it takes care of the JIT compilation and LLVM, so you don't have to. So it's a great thing to try out, whether you have pure Python code or NumPy pandas code. And the bottom line is, Numba is great because when your users or customers are actually executing your code, they might be running on a laptop like this one with 4 cores and a mobile GPU, or they might be running on a mid-range GPU, or they might be running on a cluster setup, or they might be running on Amazon, where we have the new X1 instances, right, have 64 cores and 2 terabytes of RAM. So we want to be able to take advantage of the hardware at runtime. Same code, different devices, and it compiles to those targets. So we have partnerships with Intel, with AMD, with NVIDIA that work very closely with there. So for instance, we support the new HSAs from AMD, and the Numba team is working very hard to make sure this is very transparent and that they're able to optimize as many functions as possible sort of transparently. You can also do interactive profiling. You can do interactive work with Numba in a notebook. So it works well with the rest of the ecosystem. So now I'll talk about visualization. There's some really exciting things going on in the visualization world. You might have heard of Bokeh. Of our 2 founders of Continuum, Travis and Peter, Travis was the author of NumPy and SciPy, and Peter was the author of Bokeh and Chaco. So this gets a lot of attention. There's a huge community of Bokeh, and you can check this out. There's a gallery on the website that shows basically what you get is you write Python, and it writes the JavaScript so you don't have to. What this means, it's a plotting framework, right? So you can use the charts API, very high-level API, or you can actually dig down to the primitives and use low-level things to make very custom charts. So these are interactive in-browser visualizations that are portable, or they can work with an optional server, right? So you can have streaming data being plotted. It's very easy to embed these in web applications, use them with Flask or Django, and it's also very easy to develop interactive dashboards and applications. So check out Bokeh. One issue you have with plotting libraries, right? You might have used Matplotlib or D3. No matter the tool you're using, or even Bokeh, when you start to visualize large data sets, right? So here's 70,000 tweets shown here, and you start to lose context of what's going on. Where's the real density? You're running into a few different problems. 2 of those example problems are overplotting. So we have data set A, data set B. Depending on how we plot them, we kind of lose, due to the layering, we kind of lose what the data sets are. Or you might have undersampling, where we have, for 600 points on the left, the bottom left, a certain point size works well. But if we have more points, it doesn't work so well. So it doesn't scale well with large data sets. So we wanted to look at a way for users and customers that had millions or billions of data points and wanted to plot them in a meaningful way and an interactive way. So there's an open source library that's built on top of Bokeh called Data Shader. And this is very cool because it combines sort of Bokeh and Dask, which I'll talk about in a moment, for parallel work. So it brings together big computations for large data sets that you want to visualize, and in the interactivity of Bokeh. And what it is, Data Shader is a graphical pipeline system that lets you create meaningful representations of large amounts of data. So here is a picture of the NYC, the US Census data looking at New York by race. And we can really see that we're getting fidelity there due to some transforms that we're doing, which are customizable. And we can handle very large data sets, like out-of-core, larger than memory data sets. You can check out the documentation there, and by the way, I have links at the very end to all of these tools. And some of the things you can do, you can look at, there's a data set for New York City pickups and drop-offs. There's US Census data. So I'm going to pull up a demo on Data Shader, get this running. So what this, if you go to the GitHub repository for Data Shader, there's the library available there. You can also conda install it. So while this is loading the data, if you can check out the repository and run this example on your own laptop. So this is running locally on my machine. It's importing about 2 gigs of data. This is about 12 million records for taxi pickups and drop-offs. You might have seen this data set. It was Freedom of Information Act requested for 2 years of taxi data. So here we're loading that up, and we now have it in our browser. So what we're looking at is about 500 lines of Python for the bokeh application, the loading the data, the putting the widgets in certain places. And then we're looking at data shader is handling all of the data points and the rendering as a pipeline. So what you're looking at is, we can change a few of these things, taxi drop-offs, the transfer function, the base map. So the base map in the back is just imagery. But if you focus on the data points, right? So if I enable zooming here in bokeh, I can zoom in and see. So all of these data points that you're seeing and the way that you're seeing them rendered, this is all happening live. These are not pre-rendered, so this is happening on the fly. This can also make use of Dask for out-of-core computations. So what this means is I don't lose that fidelity. It's very dynamic. I'm visualizing 12 million points on the fly. And I can change transfers, I can change spread size and get statistics. You can customize the information popping up on the tooltips. And there's lots of interesting things you can do here. So you can add functions for counts and means, just like you would in any Python application. So check out Data Shader if you're interested. We have a webinar that shows, I think they plotted 3 billion data points or something like that using the same technique and tool. So that's Data Shader. And we'll jump back now to parallelization, right? So we're kind of climbing the stack and looking at the different foundational pieces. So parallelization is very interesting. So I come from the HPC world with MPI and Fortran, long-running jobs, and trying to find a single packet that failed in over 2 weeks, and not very resilient. And you compare that to the big data world of parallelization, where we want resiliency, we want interactivity with Hadoop clusters, we want interactivity with a lot of distributed types of engines, right? So if you look at the PyData ecosystem, this is a very nice slide from last year's SciPy conference by Jake Vanderpla with the state of the stack. So if you look at the core level, there's Python, and then one level up, there are things like NumPy. One more level up, there are things like Pandas. And when you get to the top, there are things that are domain specific. So there's BioPython, AstroPy, SunPy, different libraries that all build on top of this common ecosystem. So the question now is, if you are a library maintainer or a user and you want to parallelize your code, how do you do that without rewriting everything? So it's very common in the last couple of years to just use multiprocessing or multi-threading in Python and sort of write your own parallel code, which was often kind of a nightmare to maintain and just wasn't a sustainable way for this ecosystem to be parallelized. So from that, about a year and a half ago, Dask was born. And Dask was born out of the Blaze project from Continuum, which was a funded project. And Dask was built to complement the Python ecosystem. So it was developed with NumPy, Pandas, and scikit-learn developers with those data structures in mind. And in fact, the first target of it was, how do we do distributed NumPy arrays? And then it grew into what you're going to see here. So Dask is a Python, it's a pure Python parallel computing library that's familiar. So at the core, it talks NumPy arrays and Pandas data frames. So if you're already using those things and you've kind of outgrown that on a single machine or even on a cluster, Dask is something for you because it's a drop-in replacement. It's very fast, so it's optimized for numerical computations. It's very flexible, so it can use NumPy arrays or Pandas data frames, or as I'll show later, any custom code. So you can actually wrap your code and create graphs for Dask to execute, and I'll explain that a bit more in a moment. So Dask scales up nicely. It's very resilient and elastic. And so if you have a cluster, you can scale up to 10 or hundreds of nodes and run those same NumPy operations that would fail on your laptop. You can run them on a cluster very easily. It also scales down. So if you're working on one machine and you want to make use of all of your cores. So by default, if you're using NumPy or Pandas, they're using one core, and they're going to eat up all your memory if you have a large data set. With Dask, it chunks things into small distributed tasks that it can then run on all of your cores or mini machines. It's also interactive. So I'm going to show some demos later in a notebook where we're doing interactive distributed computing on larger than memory computations, which is sort of unheard of for MPI world and batch processing world, where we just let things run that may or may not work. So we want an interactive debugging experience, and we want something where we're close to the Python code that we're running and not many levels away. So here I'm showing kind of a spectrum of parallelization. So if you look on the left side, this is where we have explicit control. We can get very fast and optimize parallel applications, but it's hard. So this is the threading, processing, MPI, 0MQ. If we're writing a high-level library for biology or finance, we don't really want to worry about all that, and we don't have to bake that into every single application. If you look on the right, there are some very nice distributed engines. So there are things like Hive, Pig, and Impala for distributed SQL. There are things like Hadoop and Spark for interactive queries and data frames. And they give you implicit control, so they're very easy, very high-level API, just like Python, but they're restrictive. So if you have custom code, it's not easy to wrap that around a MapReduce paradigm or a Spark data frame API. Dask is in the middle. The intention was that it's flexible. You can go low-level. If you're a library developer, you can parallelize your library using Dask, and we're hoping to get 80% of the parallelism and parallel code to take care of that, so you don't have to. If you're doing high-level computations and you just want to run 30 gigabyte or 100 gigabyte data sets on your laptop, you can do that as well. So it has different entry points that I'll talk about next. So how does Dask work? Dask is a distributed task scheduler. So Dask at its core is a parallel processing framework, and it has things called collections. So it has arrays, which are NumPy arrays, bags, which you can think of like multi-sets or a list with repeated elements. It has data frames, which are literally pandas data frames, and it has imperative, or what's now called delayed. This allows you to wrap custom code and create custom graphs. So when I'm using one of these collections, and I'll show some examples in a moment, when I execute an expression, Dask is going to create a graph. So if I execute a sum, it's going to break that into small pieces, do lots of little sums over many cores or many machines, and then do one final sum. It's going to create that graph, and then when I execute that graph, I can execute it multi-threaded or multi-processed or on a distributed scheduler. So it's very easy to swap between these schedulers and work on one machine or many machines, and I'll show that in a moment. So on the bottom, you see a machine learning pipeline that Dask has created. So I have a pipeline, maybe with scikit-learn, where I ingest some data, transform the data, and get an accuracy score. So you see that represented by tasks and data, and now these small discrete tasks can be executed on many cores or many machines. So what does this all look like for the end user? It looks very familiar if you're using pandas or NumPy. So a Dask array mimics the NumPy interface and implements a subset of the functionality. A Dask data frame mimics pandas. So there's nothing that I'll show on the next slides what those changes might look like and in the examples. And a Dask bag does things that look like PySpark, so we can do maps and we can do folds and we can do joins. And then there's Dask delayed, so I can wrap custom code. So I might have my own custom code that has definitions for loading the data, cleaning the data, analyzing the data. I can wrap those very easily with Dask delayed, and those are then represented as a graph that's optimized and parallelized. So it's very flexible in that regard. So now I'll talk about some example workflows of what this all actually looks like that combines a lot of the different tools I just showed. Here's a good time to mention Jupyter. So at Continuum, we also have some core contributors to Jupyter that are really pushing it so as far as it can go. So if you haven't used notebooks or Jupyter notebooks, Jupyter is a very big open source effort that has over 40 different programming languages that it supports. And it allows you to work in a notebook, in a browser environment, collaborate, interact with your data. You can share your documents, so I can create a bokeh plot. I can save that. I can put it on GitHub, or I can email it to someone. All the interactivity is preserved. So it's a very nice way to think of like a lab notebook. You sort of document your code and your results, and then share that with others and collaborate. So inside of Jupyter Notebooks, I'm going to show a couple of these examples. So the first one is distributed data frames using the New York City taxi data. The second one is distributed language processing using Dask bags. And then the other two, there are notebooks online I'll post a link to that you can find using Dask arrays, and it actually uses global temperature data. And there's a fourth one with custom code and custom file formats, right? So the nice thing about having a flexible framework is you don't have to have the exact data format that we specify. You can parallelize any workflow. If you're working with HDF5 files, or one of the new serialization formats for data frames is Feather, and it works well with Apache Arrow. So this is an example of the interoperability we were talking about earlier. So first example, distributed data frames. So Dask data frames are really composed of lots of little pandas data frames, and it matches the pandas interface. The nice thing about Dask is it has connectivity, some work we did earlier this year to connect it to Hadoop data, data that lives in a Hadoop store. So you can access data from HDFS without using the JVM. You can execute computations without using the JVM or Python Java serialization. So it's an alternative to Spark where some of our users already have code in NumPy or Pandas. They want to parallelize it. They're not sure if they need Spark or not. This is something else to look at for that. It's very fast, very low latency. So the tasks in Dask have about a 1 millisecond overhead. And this creates a very responsive user interface, right? And I'll show that right now. So distributed data frames. If it'll let me exit here. Nope, it's locked me in the presentation. Oh boy, do I have to reset the display or something here? Let's try that. I got nothing. This is what happens when you do live demos, right? So, any questions while I try to figure out what's going on here? So it's here, but it's not responsive, Nico. Yeah. I don't know. Let's try that. So was it advancing?
Is it maybe froze?
Perhaps
did
it
crash?
is. Perhaps it did. No, it's still
Okay.
it's still doing something. Yeah. Any advice here? Restart.
Yeah, maybe.
All right.
I had this once.
Okay. Well, there's a built-in break here. Any questions while I restart here? Questions about Dask? Questions about Bokeh, Data Shader, Conda? Sorry about this.
Question for NumPy.
Yes.
So when there's optimization to distribute it, can I gain from the code? So normally when I need to parallelize my code, it's hard work to do
Yes.
it. So I can use this as a kind of optimizer or at least get some hints.
So this is mainly going to be discretizing your large NumPy array into smaller tasks that can then be executed, right? So this is for, if you're running into, so for small data sets that run on your laptop, you probably won't see any performance improvements because of that. But if you need to do larger than memory computations, that's where this is going to help you. And then it's going to be executing those small NumPy operations, right, with some small overhead from the distributed part. Does that make sense? For the optimization part, that's when you could look at something like Numba to see if it would work for your use case to speed it up. So together, they can work very well. Things are serialized in Dask via Cloud Pickle. So as long as these are serializable, which most things are, just like Spark, then this should work for you. Okay, it's coming back now. Should be good. Just need internet back. Okay, looks like we're back. Great. Sorry about that. Okay, so while this is loading, I'm going to be showing first a distributed data frame using Dask as soon as this loads up. This all worked just before. I did, but I have a Ethernet here. Yeah, I can try Wi-Fi. I see something happening. There we go. Something's happening. Okay, well, let's start with the one that's working. I'm going to start with the distributed language processing using Dask bags. So what this is this is running live on a cluster. Make sure everything's up there. Cool. Okay. So we're going to look at natural language processing with Dask, and this is going to use the Dask bag interface. And so what this looks like is we have a 4-node cluster running on Amazon EC2. Each node has 8 cores and 30 gigs of RAM. We're going to load data from HDFS, and we're going to use Dask to do distributed language processing with the NLTK library. This is a natural language toolkit. And we're going to use pandas and bokeh at the end when we reduce our large data to small data to actually work in the notebook, all in the same notebook, doing big computations on the cluster and then local analysis at the end that we're used to. So we'll load in the data, we'll explore some of the data sets, we'll do language processing, and then we'll work with pandas and bokeh. So what this looks like is I'm first going to connect to the distributed scheduler. So Dask has the distributed scheduler I described before to run on many machines. So I'm running Dask workers on 3 of the nodes. So those are my compute nodes, and I'm running the Dask scheduler on the head node, and the data is stored in HDFS on the 3 compute nodes, right? So Dask, via the HDFS connectivity, is aware of where that data is on each node. So I'm going to connect to the Dask scheduler here, and you can see I have 24 cores and processes available. So it's 8 cores per machine times 3. So I'm ready to use all 24 of those cores. I'm then importing Dask, and what I'm going to do then is to load this data. So this data set is from the reddit.com website. It's all of the comments from 2007 till current. The entire data set is 1 terabyte. Here I'm going to load 1 gigabyte, which I know is not big data, but that way we don't spend 30 minutes watching loading bars, because I'm actually going to load that into memory, right? So I'm going to read one of the months. This is from 2009. I'm going to import JSON, and then I'm going to filter out from the movies subreddit or subforum all of those comments and persist those in distributed memory across the cluster, right? So what it's doing right now is loading all of that information from each of the worker nodes, and it's now in memory distributed on the cluster. There is a user interface that I want to show you that is coded in Bokeh, and it actually gives you information about what's happening on the cluster with Dask. So this is very cool. What we're seeing here is the amount of CPU, the amount of memory, and the amount of network that we're using across the entire cluster. And then we're seeing the operations that are happening right now. There's the load operation I just did. And then at the bottom, we're actually seeing the task. So this is the load data task that just happened, the filter that just happened on each node. So I'll jump over to that when we do more interesting calculations. So I now have my gigabyte of data loaded into memory. It's JSON data. And we've filtered it, so we now have that information stored across the cluster. So now I can do things really fast. So in just a few milliseconds, I can count the number of comments. So there's about 9,000 comments in this data set. One of them looks like this. So it has many different fields, has the author, the date, and then the actual body of the content. This is all happening in near real-time speed, so it's very interactive to work with this data. It would be just as fast if I had loaded the 30 gigs. We would have just waited initially for it to load over a couple of minutes. So I can then query things. So I can query for comments that contain Kevin Spacey in the body, and I can very quickly get back all of those comments. Now to the interesting part, we want to do the distributed natural language processing, right? So here I've defined a function called parse, and here I'm going to import the natural language toolkit. I'm then going to tokenize words, and I'm going to tag their part of speech. So I'm going to define that function, and then I'm going to map all of my comments that are in that collection to that function. So if we look at one of those, it's completed already. If I look at one of those, you'll see the body of the comment and then the tagged part of speech. So proper noun, verb, adjective, and so on. So now, let's say we want to extract the top 10 or top 20 proper nouns in this entire data set across all of the words, across all of the comments. So here I've defined a function to clean the data. So here we're going to only get proper nouns, and then we're going to remove stop words, and then from the NLTK corpus. And then we're going to remove sort of garbage characters, things that are not words. So I'm going to map that to my data set. And as this is executing across the cluster, I'm going to jump over to the UI, and you'll see those various tasks that are executing across the cluster. You can see the type of task, you can see how long it took, and you can see the status of what's going on in the cluster resource-wise. So that's completed, and now I can return that, now that I've reduced my big data to small data, and I can now import that back in as a Python dictionary. So then I can do regular things with pandas. I can look at the list of the top 10 proper nouns in the data set. I can generate plots from pandas. So here's a bar chart of those top 10 and their frequency. And then I can generate interactive plots with Bokeh with just a few lines of code, with 7 lines of code here. So here I'm importing Bokeh, and then I am, if it cooperates with me, I may have to jump to the other notebook, would have an interactive interactive Bokeh visualization to show at the end there. So I'm going to jump forward here, in the interest of time, and jump over to the distributed data frame computation that wasn't cooperating with me earlier. So now we're going to do a very similar type of analysis. We're going to use data frames distributed on a cluster. And I want to kind of show the flexibility here if you're a pandas user or have a different use case, how Dask could work for you. So here we're going to load data. This is in New York City taxi data. It's about 20 gigs of data for taxi pickups and drop-offs, and stored in CSV format. So here I'm going to just query the data like we would on a single machine. So if I look at the different files that are available and maybe get the head of one of the first files, I can see things like pickup date, drop-off date, passenger count, distance, things like that. So now we're going to do that distributed on a cluster. So I'm going to start up again and point to the Dask distributed scheduler, and then I'm going to import Dask data frame. So a Dask data frame is just lots of small pandas data frames. Once I've done that, the interface is exactly the same as pandas. So read CSV and parse dates and header, those are all things from pandas. So we're going to load in 20 gigs of data across the cluster distributed in memory. And again, I can jump over to the UI. I can see all of my cores spinning up. I can see this memory slowly increasing. So I'm loading all of these things distributed. I'm executing that task graph across the cluster, right? All in pure Python, all very interactive and close to the computations we're doing. So after about 30 seconds or so, we will have 20 gigs on disk, 60 gigs in memory loaded up and distributed across the cluster, and we can do very, very fast queries. Another thing to notice is while that computation is running, I can actually do things. So I'm not blocked by that operation. So this is great for interactive work. So I can look at the different columns that we saw earlier. I can look at the data types that pandas inferred from the samples. And then it's just like I'm using pandas. So I can do a head and get different columns. I can do some analysis like I might do in pandas. So let's say we want to know what types of tip fractions are given and how do taxi drivers report tips. So I'm grabbing 3 of the columns, the fare amount, the tip amount, and the payment type. So payment type here, I believe payment type 1 is a credit card or debit card. Payment type 2 is cash. And I'll jump through a few of these calculations. But basically, something we see is that when we calculate a statistical correlation, we see that payment type 2 pretty much has a tip of 0 every time. So cash tips not reported for some reason. And if we look at tips collected by the hour of day, so we want to know, does this vary at all by the hour of day over the entire couple of years of data here? So what we're going to do is we're going to exclude payment type 2 because it's a little bit shady that no tips are reported there. We're going to exclude things that have a 0 or less tip amount, and then we're going to calculate a tip fraction. So this is just the tip amount divided by the fare amount. And we're going to perform that computation distributed on the cluster. So you can see that happening across the cluster very fast, very low latency. And when that's done, so that was on 60 gigs of data in memory, we can plot the result in bokeh. And we see here that the highest tip fraction, about 35%, happens at about 4 a.m. Anyone have any guesses why? Anyway, nonetheless, this is an interactive plot that we can zoom in the data, we can select the data, brush the data. I can save this notebook. So in the same notebook, I did cluster computations, local computations. I can save this, email it, put it in GitHub. All of the interactivity and data that you need to do this is all preserved in here. So that was the second sort of interactive demo here. Let me get back to the presentation part. OK, great. So we covered those demos. And natural language processing, we walked through that. It looks like Spark and Hive. It's very interactive. This handles sort of the standard computations that you might do on a set or a list. Distributed arrays, so I won't show this notebook, but it's available at one of the links that I show at the end. This is where we use NumPy arrays, and we can work with different types of data, maybe HDF5, and we can do custom algorithms and things like that, all built on NumPy arrays. Or if you have really custom workflows, you have a file format, the new file format, or just your own code workflow, you can wrap that with Dask delayed and create a Dask graph and have that executed in parallel. So in summary, scaling up and scaling out, we hope that's easier with things like Numba and Dask. So on a single machine, you want to use all of your cores, you want to use GPUs. This is where Numba and Dask both can help you for parallelizing multi-core, multi-threaded computations and optimizing for different CPU or GPU targets. For scaling out, this is where we hope that Dask and distributed can help. And really the combination of both, we have users and customers that are using large GPU clusters. They want to make the use of that hardware as much as possible. When you think about Python and Hadoop, there's a couple of different ways we integrate. So with PySpark, you can use Anaconda just like you would. So you're able to import libraries. If you're able to install it and provision it on each node, you can use PySpark and Anaconda. They work well. Or if you are interested in, or you already have Python code with NumPy and Pandas, you can use something like Dask and distributed, and you can even interact with data on HDFS and do sort of scientific or numerical computations that are interacting with data from HDFS. Both the data retrieval and the computation is all executed without the JVM and without the need for the Python Java serialization. So the open data science stack, now that we've seen all the tools, when it all comes together as a platform, it can look something like this. This is sort of one example, but we might have a server, bare metal, or in the cloud, or a cluster. And then we might have data living in many different places. Maybe it's in HDFS, and we're using Yarn for resource management. Or maybe we're using a HPC cluster with SGE or Slurm. And we do have users using Dask in production in all of these setups. And then for parallel computation, you might have Hadoop installed, and you might have Dask all sort of working well with each other, all using Yarn. And then what you get on top of that from Anaconda are many of these open source libraries that I mentioned. You get pandas, NumPy, SciPy, Numba, and so on, scikit-learn. So there are some libraries like scikit-image that now depend on Dask. So when users are doing image processing workflows and pipelines, it's actually sort of parallelizing it for them all behind the scenes, which is really nice. Or you can do things like I showed today, sort of interactively. And then at the application layer, you're using something like the Jupyter Notebook to bring this all together and share it with your colleagues. So these are the open source components that I pointed to today. There's many more. There's new ones incubating. But I think these really make up the core of what we do and address these different verticals. Here are a bunch of links, and I'll tweet out just after this talk a link to these slides. So please check out all of these open source projects, and we're very happy to hear about how you're using them and how Anaconda is solving your problems and making it easy for you to spin up data science and analytics use cases. And all of the notebooks are posted online, and check out our project. So thanks so much for your time. I really appreciate it, and look forward to talking more with you. I'll be out at happy hour. See you there. Yes, any questions? Thank you. Yes.
So it's amazingly fast. Can you also deal with like streaming data or updates?
Yeah, that's a very good question. The question was, can you deal with streaming data or updates? We're very light on this right now. We're doing some experimental work to see if that makes sense. The better news is there are clients for Python for Apache Storm, and of course Spark Streaming has PySpark. We would recommend those at the moment for streaming. Those are very robust and have nice official or unofficial Python clients to use, which once you bring it in, using one of those clients, you can then do many of the other things I showed here. So it may be the case that you're using, some of our users are using Apache Storm or Spark Streaming, and then using Anaconda or Dask, like when it makes sense. So again, best tool for the job. So we're experimenting with it, very, very early and young to say that we would do that. I would lean on one of those frameworks and use their great Python ecosystem. Yep. Thanks, great question. Any other questions? Yes?
So how exactly does Dask compare then to Hadoop? So is it just a matter of language choice, or?
Right, good question. So the question is, how does Dask compare to Hadoop? Is it just a language choice? So Dask was architected, again, for the goal of parallelizing NumPy arrays and pandas data frames. It's pure Python. It uses Tornado for communication. It uses ZeroMQ for communication between nodes. And it uses directed acyclic graphs, just like Spark. So it's really an implementation where we wanted to work and complement all of the things in PyData and numerical Python, scientific Python. The connectivity to Hadoop here is about data. So I showed loading from, there's actually a C library that we use, or a C++ library that Pivotal released called libhdfs3. We wrapped that in Python, and now we can access data in Python, which is very exciting. And soon there will be Parquet support in Python. So really this is just a pure Python execution framework that's flexible. It can do things like text processing, things that look like batch processing in Hadoop. It can also do other things like numerical computations, scientific computations. So we see it as a more flexible alternative that complements PyData. Any other questions? Yes?
So it's not a technical question, it's more a business question. What is the business model of Continuum Analytics?
Yes, what is the business model of Continuum? So Continuum does 4 core things. So we support open source software. We also have enterprise software to help people use Python in the enterprise. These involve cluster, managing Anaconda on the cluster, managing notebooks and enterprise collaboration. We also do support, and we also do training on these things. So these foundational things have been worked on for a very long time, and they have their own active communities. Again, like was said, I think in the previous talk, and we don't drive those roadmaps, the community does. Anaconda is just our way to package all that up And with things like Conda Forge, it's very clear that there's a lot of community involvement and a lot of users benefiting and contributing back to the Anaconda system. So that's why we have, like I said before, a portion of our developers that are full-time open source developers, and we have others working on consulting solutions and training and so on. Thanks. Any other questions? Yes?
You said if I execute some task, it doesn't block other tasks, so I can start more. Can I also give them like priority, or is that all up to Anaconda and I'm left?
Yes, so you're asking about task prioritization of tasks and how, so I mentioned that it wasn't blocking, but can you assign weights and priorities there? So Dask internally is using some prioritization depending on data locality, depending on size of data, chunks, things like that. So most of that's done behind the scenes, and some of it is user accessible, but most of this is done sort of as the DAG and the directed acyclic graph and optimized. But I would say there are pieces you can weight there. Mostly we use them internally, but they are exposed if you like to dig down to the low level. Yeah. And this comes in handy when you're doing the custom workflows, right? So you might have loading, and you might have tasks that look the same in a custom workflow, but you need to actually weight them accordingly. So it is possible to do that. Great. Any other questions? Great. Thank you, everyone.